It's about heat treatment of steels. Right? So we have this steel bars which are of different types, used in like a construction purpose. Maybe this mild steel or hard steel or red hot steel. There are different types of steels. We'll see how we will prepare them and what's the difference between these steels, right? So you will have in your practical also. All right. So heat treatment of steels. Common steels which are really solid solutions of carbon in iron are body-centered cubic. Okay. So there are different structures for different phases, right? Phases in the sense, say for example, in the structures, while you're studying structures, BCC, FCC and all, you might have seen the examples, right? Some of them, I gave an example of like alpha Fe, all right? Alpha Fe or beta Fe, right? Or maybe gamma Fe, all right? So what does this Fe is? Yeah, ferrous. So there is iron, right? So either you can say it as ferrous or iron, all right? Right. So this iron will take different forms under different temperature and different conditioning, all right? So some cases it will be of like alpha Fe, alpha ferrous, or beta ferrous, or gamma ferrous, or delta ferrous, right? So this is not only for Fe iron, so that we use commonly. For most of the metals, we have this, right? So the structure is actually varying. Say for example, if alpha Fe is of BCC, I'm just saying for example, then beta Fe will not be of FCC, that may be of BCC. All right. So that's the difference. So when we go for heat treatment, what we do is we change the phase. Right? Change the phase mean either we have it in alpha phase or beta phase or gamma phase or some mixed phase, right? Along with some carbon, right? So common steels which are really solid solutions of carbon in iron are body-centered cubic. So mostly they are of body-centered cubic. I will deeply say when we are going forward which structure having which structure, right? So probably we have carbon mostly in the iron. Right? There are other metals also in a very less quantity, maybe in 0. quantity, but usually carbon and iron combine to make steel, right? So that's what we do in heat treatment. There are different heat treatment procedures, right? Different types. However, the carbon has low solubility in BCC iron, right? Carbon has low solubility in BCC iron. If metal A and metal B, if we need to mix it to form a kind of alloy C, right? So these two need to mix for certain extent, right? These two need to mix. So if I consider this as the alloy C, so maybe these blue particles are of metal A and these green particles are of metal B, possibly, right? So these need to mix together. But there is an extent for which we can go for, right? So we can't go for 50-50, right? For some metals we can go for 60-40, for some 70-30. That will vary, right? So for every two or whatever the mixture we have, maybe it can be of 3 or 4 materials we are mixing, but there will be of a kind of solubility will be there, right? Solubility in the sense, say for example, so you are mixing, say for example, you are preparing a lime juice, lime, sugar, water, salt. Okay, so I will put salt also, right? So these are these 4 salt. Yes, these are these 4 major ingredients, right? So there is a limit for how much sugar we can put, how much lime we can add, how much salt we need to put, and how much water we need to put, right? There's a limit. So their water need to be, for example, say around 85%, right? Then lime may be of 5%. How much is that? 90. Sugar may be of 8%. and salt may be of 2%, right? So this probably will make lime juice. That's fine. What will happen if I put 85% of sugar and 8% of water, and rest 2 will remain same? So how will this look like? How do you feel this? 85% of sugar and 8% of water. Will it look like lime juice? No, right? So that may look like a kind of hydrated sugar. Hydrated sugar, you know, like some moist sugar, right? So when you vary the constituents, what you are preparing is differing. So if you are preparing for lime juice, you need to go for this quantity. If it is like hydrated sugar, then you may have to go for this quantity, right? So based on varying the constituents, right, individual elements, what you are preparing is varying, right? So the similar case will be applied in the case of preparing alloys also, right? So for hard steel and mild steel and soft steel and all, the percentage addition is different, right? So we'll see what is the percentage addition for which structures when we are going down, right? So I just need to explain. I just want to explain you that while varying the individual constituents, the percentage, you will have different materials, right? Final products, right? However, the carbon has a low solubility in BCC ion, precipitates as iron carbide when steel is cooled from 870 degrees Celsius, right? Low solubility in BCC ion, right? So when this happens, right, 8% water, 85% sugar, this is not going to solve in this, right? This is not going to mix in this. Maybe for like 5 or 6% will mix, but rest 80% will remain as like sugar. So here also carbon, right? The carbon has low solubility in BCC ion, right? So BCC structure, you know, body centered cubic structure ion. So in that structure, carbon does not have good solubility. It has a low solubility. As iron carbide when steel is cooled from this much degree Celsius, right? So this temperature and everything, you don't need to worry now. That we will go deeper into like when coming to the next slides. All right. The process of precipitation can be altered by adjusting the cooling rate, right? So about the cooling rate now we will see. Say in like normal conditions, when you mix 85% sugar with 8% water, say for example, your 5% sugar got mixed, right? If you heat this, right? If you heat the same thing, so I'm using again 85% sugar and 8% water. So why I'm stopping with 85 and 8, 93, only 93 is here. There are another 7, that is 100%. So I left it here because there can be some other constituents or mixtures also, right? So that's why I just keeping in this format, right? And I heat it, okay? Heating we use like arrows like this, or you can write heat also here. So what do you think? What will happen for this 5%? Will it increase or decrease or remain same? So this 5% is the mixture, right? Mixed sugar. So when you heat this, what will happen? Will this 5% solid sugar will increase, or will it decrease the solubility, or will it remain same? So here that will increase the solubility. So maybe it will go up to 8%. So based on this example, we'll again come to this statement, right? The process of precipitation can be altered by adjusting the cooling rate. So altered mean either you can increase or you can decrease, right? Altering, that is changing, right? Adjusting the cooling rate. So cooling rate is a kind of temperature, right? You know, it's a kind of temperature. So maybe by increasing temperature, you can decrease the precipitation, right? Something like that. So precipitation mean again, do you know about precipitation? Precipitation is like when you are mixing A and B, so water and sugar, right? So there would be some sugar mixed, right? And there will be some sugar at the bottom, right? So this sugar which does not mix is what called as precipitate. All right. So when you are mixing two things, whatever the item which does not mix and stay like in a different phase will be called as precipitate. So in this region, that will be is of sugar plus water, but here that would be of only sugar, right? That's what the meaning of precipitation is. It can be altered by adjusting the cooling rate, right? So cooling rate in the sense you can alter the temperature. This changes the distribution and size of the carbide, which forms a laminar structure called pearlite during slow cooling process. So you do not wonder about the word pearlite. That's a structure that we will study when we are going down in these slides, right? So when you are heating, if the percentage increasing, which means either the amount of mixing salt should be increased, sugar, or the size should be increased, right? So changes the distribution and the size of the carbide, right? So distribution is more amount of that carbide mixed with iron, and size big molecules, right, or big atoms mix of a carbide, which forms a laminar structure called pearlite during slow cooling process, right? If a steel is quenched into water or oil from this many degrees Celsius, a metastable state called Martensite forms. Again, do not worry about the word Martensite, pearlite. These all are different status of iron that I will explain when you are going down these slides, right? Which is body centered tetragonal. So again, if a steel is quenched into water, so here we are doing slow cooling, right? Slowly we are cooling it. But what we are doing here is we are cooling it in a fast rate. So which will form a metastable phase. Metastable means it is not very stable. Okay, it is in between two phases. Say for example, you have phase A, right, and you have phase B, right, and in between these two phases, that will be of metastable, right? If the steel is quenched into water from this many degrees Celsius, a metastable phase called Martensite forms, which is body centered tetragonal. So here it is body centered cubic. This is body centered tetragonal. So these are different, structure. This phase setups large internal stresses and prevents carbide from forming. So here what happens is this state martensitic forms of metastable set up large internal stresses. Right? So this will have internal stresses. So maybe some forces in the internal and prevents carbide from forming. So this will not allow to carbon to form. The internal stresses produced a high hardness and unfortunately low toughness. All right. So the relation between hardness, toughness, stiffness, these all we will see later, right? So when you cool it suddenly, the hardness will increase, but the toughness will decrease. After cooling, to restore toughness, steels are tempered by reheating. Okay. So again, tempering means this is another form of heat treatment, right? Another form of heat treatment by reheating them to a low temperature around 426 degree. So you have it in a high temperature, you cool it down very fast, and then again you heat it slowly to this 426 degree Celsius. The tempering relieves the internal stresses and also allows some iron carbide to form. It also restores ductility. So, for example, say you have only a small gate, right, to enter. If like 10 people are coming, that's okay, you can enter. But at a time, if 1,000 people come and want to enter, right, what will happen? There will be rush, right? There won't be any regularity in this, right? So 1,000 people will come. Say for example, this is a gate, right? And they will rush here and there, right? And maybe the coming out would be like 1 or 2, right? And then say for example, if somebody is there to regulate, okay, you guys stay in line and then go one by one, then this flow would be fine and less time consuming. Okay, so similar thing happening here. The temperature is of very high, around 870, and you put it into water, right? So which means it is coming to 30 degree, right? That's the water temperature in like normal environment temperature. Say for example we go for 30. So 870 degree to 30 degrees Celsius in like few seconds. Say for example 2 seconds. You just have to take it and put it in the water. So you just imagine how fast the cooling rate is, right? So in that sense, there won't be any arrangement and regularity in between the interior materials, right? Interior atoms. So they will just like uh, obtain the space whatever available, take the structure whatever available. That's why it is very hard, but tough is less. So due to that, what we do again, we heat it slowly to this 426 degrees Celsius. So why we are going for 870, why 426, why can't we go for 530? So these are different stories that we will study when we are coming down the slides, right? So when you give some extra heat, now they will arrange themselves to make some certain space, right? So you can get, I mean, this carbide can get space, right? Reheating them to a lower temperature, the tempering relieves the internal stresses, right? So this will regularize the atoms inside and also allows some iron carbide to form, right? So if space is available, then this iron and carbon can combine to form the iron carbide. All right. It also restores ductility. So ductility, you know, the property of metals, right? So this will restore ductility. But when in this state, that will not be ductile, that will be of brittle. Okay. So when you put it in the water, that hardness is there. No, where is hardness? Yeah, high hardness. So if a material has high hardness, which means it has high brittleness, so that will break immediately. So this is the phenomena of two major parts of this is rapid cool. Sorry, this is slow cooling, and this is fast cooling. And then we have like small variations in between here and here. That's a different story. We will go deep into that now. For now, what will happen if we go for slow cooling, and what will happen if we go for fast cooling, right? If we go for slow cooling, then material would be soft and brittleness will be low, ductility would be high, hardness would be low, toughness would be high, right? If we go for rapid cooling, all the above properties is opposite to what I said, right? So this is just the introduction, right? So these are different heat treatment processes: annealing, tempering, and then we have hardening, right? So here, what does this annealing mean? The hard red hot steel 700 to 800 degrees Celsius is allowed to cool at room temperature very slowly, by which hard steel become soft, right? So here we are making the hard steel to soft, right? So that's the purpose of this annealing process, right? Red hot steel is allowed to cool at room temperature, right? Very slowly. All right. So we will see how to do this. So for annealing, what we do, we heat this rod, right? Iron steel rod to a certain temperature. So here this is 700 to 800. There are specific temperatures, right? A range, right? You can go for. So you heat it, right? And very slowly you will go for cooling, which means you just off the fire, right? You off the fire and you let it cool. So you will not do anything for that. You will not take it out of the furnace. You will not put it in the water. You will not have it in the air. You just put it in the furnace, right? Say for example, this is a furnace. You put this one to heat, right? You provide fire, right? And once it reach the temperature 800 to 700, sorry, 700 to 800 degrees C, you will leave it, right? You will leave it as it is. So when you leave it, what will happen? You are off the fire. So this one will, what will happen? The temperature will reduce gradually, right? Maybe it will take 3 to 4 days. So this will take so much of time to come to the room temperature, right? So the cooling curve would be like of high time consuming, right? This will be of very less slope. Maybe 3 to 4 days it will take to cool down, right? So that's why it's mentioned very slowly, right? Very slowly. So here we are having a hard steel, but what we are doing is we are making as soft steel, right? Soft steel. So for purpose of annealing is making a soft material, right? This is how annealing is done. So you heat it, have it in the furnace for a particular number of like until it comes to the room temperature, right? Then I have tempering, right? The hard and brittle steel is heated to a temperature much below redness and cool very slowly to the room temperature, by which brittleness of the steel disappears while the hardness remains same. So what you do, you have it, I mean you heat it, right? And you put it in the water, then you take it again and heat it only up to this range, maybe 200, 300, 400, that range. You will not go for 700, 800, right? You will heat it very slowly. No, not heat it very slowly. You heat it and you leave it to cool slowly, right? And cool very slowly to the room temperature, by which brittleness of the steel disappears while the hardness remains same. So this is done to increase the brittle, not increase the brittleness, reduce the brittleness. Brittleness is breaking immediately, as like glass, right? So we don't want that property to occur in this steel. So what we do, we go for tempering, right? So when we do this tempering, this brittleness will disappear. So which means it would be of like good hardness and good ductile property. So opposite of brittleness is sorry, not hardness, ductile. Okay. So ductile is the property of metals. So when you heat it, that won't break, right? That will increase in length, volume, or area, right? So that's what ductile is. Brittleness is of glass, that will break immediately, right? So this tempering is done to remove brittleness while having the hardness same. Okay. Quenching or hardening. So in this hardening, we have two types: case hardening and another type of hardening, right? So we'll see what is this quenching or hardening is, right? So this is the process which happened before tempering. The soft red hot steel is cooled suddenly at room temperature and immersing into water or oil, by which the steel become hard and brittle, right? So what will happen? You heat it to a high temperature around 700 or 800, right? And then you suddenly take it and put it into this water bath or oil bath or some salt bath, right? And you make it like hard, right? But what happen is hardness will be increased, at the same time brittleness will also increase. So since we do not want brittleness to be there, we go for tempering. So actually before tempering, what we do is quenching or hardening. So these two are same, right? So red hot steel is cooled suddenly at room temperature and immersing into the water or oil, by which the steel become hard and brittle, right? So this is quenching or hardening. In this, there's one type, case hardening, when mild steel is heated with charcoal and plunging into oil. This makes the surface layer hard due to formation of iron carbide Fe3C. Right? So this iron carbide, cementite, you don't need to worry about these words. Now we are going to study up them, right? So what will happen? Case hardening means you heat it with the charcoal, right? Charcoal. So charcoal, you know, it has carbon, right? It has carbon. When you keep the iron rod and surrounded it by charcoal, and when you make it burn, the charcoal and the carbon on this carbide in this charcoal will little bit penetrate into this iron, right? It will penetrate into the surface of this iron. So that is why it is called case hardening, right? The case, you know what is a case is, right? If you have something and if you keep it in the case, that is the outside, right? Outside in the sense like a kind of layer, right? That's why it is called as case hardening. So when this mild steel is heated with charcoal, right? You put charcoal and plunging into oil. So plunging into oil is you heat it and then put it in the oil, right? This makes the surface layer hard. So here we particularly focusing on the surface layer, right? So particularly focusing in the sense, say for example, you have this big steel, right? You can vary for which thickness you need this layer to go into, right? You can increase this thickness by varying the time, right? Varying the temperature, right? Varying the charcoal content. So there are different procedures. So if you just want it for 1 millimeter, you will have different time, different temperature and different charcoal content. Say for example, you want the layer to like be hard for 2 millimeter, right? So I'm just giving example, right? So in that case, you will have different temperature and time, right? That will vary. So in that case, what we do is, so how is this different names like mild steel, hard steel, red hot steel, right? These all are coming from, right? So you can determine to how much thickness you need this case to be hard, right? And there are numerical, I mean, formulas also, all right? But you don't need that deep, right? You just have to understand we can alter the thickness, right? This is what called the case hardening, right? This makes the surface layer hard due to the formation of iron carbide, right? This iron carbide Fe3C is a hard material, okay? So Fe is your iron, right? That's here. Charcoal is carbon, right? So when this carbon react with iron, that will form a kind of Fe3C, which is called as cementite also, or iron carbide, right? So that will be of high hardness, right? That will form only on the surface and which will be of high hardness, right? So this is what the meaning of case hardness is, right? Then we have nitriding, all right? So here we go for carbon addition, but here we go for nitrogen addition, right? When the mild steel heated to 550 degrees in the dry ammonia gas, this makes the surface layer hard due to the formation of iron nitride, right? Iron nitride. So here it's formed as iron carbide. Here we form iron nitride, right? So case hardening and nitriding. So this iron nitride is also a hard material. So here we have ammonia gas. Ammonia, you know the formula is NH3, okay? NH3 gas. So you heat it with this ammonia gas, right? When the mild steel heated to 550 degrees Celsius, okay? So in these cases, temperatures are very important. You can't just arbitrarily heat for different temperatures. There are specific particular temperatures for each process, right? So when the mild steel heated to 550 degrees is a dry ammonia gas, this makes the surface layer hard due to the formation of iron nitride, right? Iron nitride, all right? So these are the differences between heat treating process, right? Heat treatment process. We have annealing, which is slow cooling. We have quenching or hardening, that is fast cooling. And we have tempering, which is fast cooling, then slow heating and slow cooling. All right.
What is the difference between hardening and annealing? It's annealing means
Yeah,
increase.
annealing means slow cooling, right? So we heat it for a certain temperature and we leave it to cool for like slowly. So the rate of cooling is low. We keep it in the furnace and we leave it. So it will take like 1 or 2 or 3 days to cool down. Right? That is annealing. While hardening is we heat to the temperature, but immediately we take it and put it in the water. So which means the cooling rate is very high. Within 2 or 3 seconds, it will reach the room temperature. But in the case of hardening, that will take 2 or 3 days to reach the room temperature. So annealing will make the metal soft, while hardening will make the metal hard.